All right, good afternoon, everyone. Thank you for coming to our session. The mic is moving around a bit. I apologize for that. Okay, thank you for coming. Who's here at re:Invent for the first time this year? All right.
Awesome.
There's a number of you. Welcome. It's really good to talk to you today. I'm Cami Tavares. I'm Director of Product for Elastic Block Store, and I'm here with Mark.
I'm Mark Olson, Senior Principal Engineer on Elastic Block Store.
So we have a very packed agenda today. I'm going to cover it really quickly and just dive straight into it because we developed some really great new content about resiliency on EBS, and we want to make sure to cover it all. So I'll start with a few concepts and constructs that we use at AWS all the time when we're talking about resiliency, just to make sure we're all starting from the same point in terms of thinking of availability zone independence and failure domains and things like that. And then Mark will talk about how we've applied these concepts and some techniques to build resiliency into EBS over the last almost 15 years now. And then I'll come back and tell you a little bit about some capabilities we have that you can take advantage of when you're building resiliency into your own systems and applications. And then Mark will come back and cover some real-world examples of how these best practices and techniques can be applied to some resilient architectures, examples that we really like. With that, let's get started. So as I said, I'll cover some real quick concepts related to resiliency. And when we talk about resiliency, what we're really talking about is making sure your application is available when you need it. And there's a few mental models I want to cover. First is really understanding your risks and the potential disruptions that your application may be subject to. There's also some things we can do to minimize the scope of impact. And this is really about asking ourselves, if this application is unresponsive, what else would be impacted? And then coming up with ways to try to contain that impact as much as possible. And then we'll talk a little bit about recovery and some things we can do to expedite that as much as possible. So we've been building and operating large distributed systems in AWS for a few years now. And you'll learn some things pretty quickly through that experience. One of them is there are some fundamental properties of our universe that we really just have to contend with. And I'm talking about some annoying little things like the laws of physics and the speed of light. And perhaps the most annoying of these properties of this universe is this one, which is an observation by a guy called Murphy. And basically means stuff breaks, right? And things will inevitably fail. And I don't know if that's been actually proven, but it's been true in my experience. And so let's talk about some ways that things might fail. We have, of course, component failures. Servers crash, a disk will fail in many interesting ways. You may go completely offline. You may do some random IOs. Network devices can fail. They can introduce random bit flips. Outside of the data center, you can have things happen that can cause infrastructure events, right? You can have a utility worker that may accidentally cut some fiber, or a storm can cause a power outage. In more extreme scenarios, you can have physical damage from floods or fires. And then there's also non-physical failures that we have to worry about. And these typically manifest in the form of load stress on your system. This can be from a demand that you underestimated. You've built something really awesome, and you have this sudden surge in traffic. It can also be because a failure in another system is causing an overload on your system, a DDoS attack. And there's also what we call poison pills. And you can think of these as particularly problematic requests that are either really expensive, or there's something about them that trigger a bug in the system. And then these can be pernicious because a client will retry that request, right? And if it doesn't succeed, a single failure can just cascade down and impact the entire system. So I spent a lot of time thinking about these potential poison pills. And then, of course, understanding your risks, you also have to think about your own architecture, right? And understanding your dependencies. Think really carefully about hard dependencies that can translate to an interruption in your service. And then maybe there's some ways you can turn hard dependencies into soft dependencies. You can try to compensate that for them, for a failure in them in your own design. And then recognizing the properties in your environment is also super important when we're talking about understanding risks, because you can have a network topology or capacity risks, network latency that can delay your recovery. So having a good understanding of that is also important. And so security, availability, durability, these are super important for us at AWS. In fact, they are our top priority. And yet, we have to contend with Murphy's Law. So a key tenet for us is to assume that things will fail. And we design to accommodate for that potential failure. So when things do fail, we try to minimize that blast radius as much as possible. We work relentlessly to prevent failures, and I'd say we've gotten pretty good at keeping our systems extremely highly available. But we also relentlessly focus on blast radius reduction for those rare cases when Murphy's Law does strike, and then we have a failure and we need to contain it quickly. So we use the term blast radius because failures are not really binary, right? It's not just failing or not failing. There's usually a degree of impact. And the term blast radius can help us convey that. Some of the ways we think about blast radius and how to reduce it at AWS is to ask ourselves how many customers would be impacted, what workloads would be impacted, or what functionality in this system. Is the functionality completely unavailable? Is it partially unavailable? How many locations? Is it a single rack in a data center? Is it an entire data center? So asking these questions really help us understand the potential scope of impact and how to contain it. And then the last mental model or concept that I'll want us to think about throughout this talk is recovery. Because when we're doing a resiliency assessment of our applications, it's really important to understand the context of the specific workload. And here again, asking ourselves this question is super important and helpful. What systems break if your service is unavailable? We ask this question not just to figure out how to minimize the scope of impact, but also because we have to factor in that business criticality, right, when we're making decisions about what course of action to take in a recovery. I really like this diagram. It's from our well-architected framework website. If you haven't checked it out, you should. There's a lot of good content in there. And so we have an event that they're in the middle. And what happens after that event is downtime. And so thinking about defining a recovery time objective will help you understand how long the systems that depend on this data can tolerate downtime, right? So answering that question will help you define the RTO. Asking yourself, what is the cost of downtime, will help you define that RTO as well. And for critical systems, the cost is usually very high, the cost of downtime. And so we usually try to find a way to continue servicing the workloads requests during recovery. And that means an RTO of 0. And then we also have the recovery point objective. And that helps us understand the maximum acceptable amount of time since the last data recovery time before the event. And to define the RPO, a couple questions we like to ask ourselves is really, how much data can you afford to recreate or lose? And that will help you define that too. Now, you may be wondering, why not set an RPO and RTO of 0 for everything? And the answer, of course, is cost. You may choose for critical systems to scale for peak instead of your average to limit your capacity risks. Or you may have an active-active or an active-passive solution. But there are many systems that are not business critical, right? And so this can be an ETL job or a finance pipeline that runs in the night so people have the data that they need when they come into the office the next day to do their jobs. And if you have an hour of downtime in that workload, in the middle of the night, nobody really notices as long as the data is there in the next morning. So there's a lot of factors that go into deciding your recovery requirements. And the important ones that we really think about is what is the function of the workload resources and data? 2, what is the probability of customer impact and business disruption? And then, of course, the cost of recovery, because the solutions for critical systems, they cost more. So regardless of your recovery requirements, planning recovery is really important, and that's something that we're going to talk about too, some ways to do that. Now, of course, all of this looks different in the cloud and in an on-premises environment, so Mark's going to talk about some of that.
Cool. Thanks for walking us through some of that. There we go. So all the things that Cami just went through apply to both on-premises and AWS. But on-premises, they're harder, expensive, and more time-consuming to think about. In addition to worrying about your application, you have to either build up domain knowledge in each one of the core areas of infrastructure or be satisfied with the consequences. Now, you may have long-term service contracts with network and server vendors. Depending on your needs, you may even have spare hardware laying around, additional online capacity, whether it's network or compute to scale for peak, just in case something happens. Remember Murphy. You think about hardware life cycles and the financial impacts of carrying that spare hardware around. You also have to think about if you're operating multiple sites. There's a lot of non-obvious overhead when you're spanning multiple data centers, whether it's right next to each other across a parking lot or across the city or even across the country. A lot of shared fault domains creep into that, and you have to actually be cognizant of all that. So when you think about what it takes to run applications, like I like my stacks, and so I built a stack of pancakes here. What it takes to run applications that power your business, there's a lot of things happening. Not only do you have to be experts in your domain, the one that runs your application, but in all domains from the ground up. Now, moving into AWS, the cool thing is that you can let us be the infrastructure experts while you focus your resources on how you can add value to your business. You don't have to worry about managing capacity, all the infrastructure complexity, and the costs that come with it. Let's dive into what that means. So as Cami mentioned, we learned a lot of lessons about infrastructure. Now, many of them are documented in the Amazon Builders Library. Some of those really only apply to higher scale things, but a lot of the lessons learned can apply to any scale of deployment. Now, one area where we spent a lot of time is making maintenance transparent. And so this is part of our infrastructure management, how we think about software deployments. Our software is designed to be upgraded and patched with minimal downtime. So we know that spare hardware is inefficient. You don't like to carry it, we don't like to carry it. So we rely on live update, which means that all the software that runs in the infrastructure can be updated with no noticeable impact to your workloads. Now, when hardware failures happen, and they do, in most cases, we're able to actually take your EC2 instance, migrate it onto a new set of hosts without you even noticing. Now, our focus is mainly about resiliency in this talk, but it's important that I take a step back here and mention that our scale also affords us the ability to be more efficient. Efficiency comes in many forms, but ultimately it means that it requires fewer resources to achieve the same goal. And using less not only saves money, but it's way more sustainable. One of the most important advantages of the cloud when it comes to resiliency is the avoidance of single points of failure. That's one of the bedrock principles of services that we design in AWS. We avoid single points of failure in our underlying infrastructure. And the best way to explain this is to talk about availability zones. Now, availability zones typically consist of one or more data centers located in the same regional area to enable high throughput and low latency networking. But availability zones are independent from each other. This means they have independent connections to utility power, standalone backup generators, other utility mechanical services such as cooling, and also network connectivity. Not only is the physical infrastructure independent, but we also treat the software and distributed systems in those availability zones as independent. So this is great, because when we deploy software, we treat each availability zone in a region as a separate stage in our deployment pipelines. And so we don't move on to the next availability zone until the safety checks pass for that deployment. As we'll see in just a moment, We treat AZs as an isolation boundary for the blast radius control in our systems. This independence and the service operating principles around it allow customers to increase their resiliency by deploying to multiple availability zones, not having to worry about the fault domain, something we strongly recommend. There we go. Now, our scale is an advantage for your applications. You're able to leverage it for that unexpected spike in traffic. Whether you have a scale-out architecture, you can add more capacity, either by scaling up to increase the size of your compute if you're vertically scaled, or scaling out if you've got a horizontally scaled service. The scale and the availability of hardware based on an API allows you to react quickly in a time of need, without worrying too much about whether that capacity will be available. However, you do have to make a choice. And this is an important one, especially when it comes to things like cost, which we're all pretty conscious of these days. You likely want to keep some amount of surge capacity online to handle those unforeseen spikes. But how much? If you have too little, your application may fail and you won't be able to respond. We used to call it slash dotting. I don't know if it's, anyway. But if you have too much, your costs are going to increase. So the cloud allows you to experiment. You can test these different workloads. We recommend that you do, but one word of caution. It's really hard to account for and simulate every single failure. So the most important thing, even if your test results give you something that's interesting, is to have a decision plan or a decision framework so that you can make the decisions ahead of time when you have to fail over or do something that's unknown, outside of the stress of that scaling event. Now, this talk is really about EBS resiliency, so let's dive in a little bit more into storage. How many people are using EBS today? I should see every single hand in this room up, because most of you are probably using it whether you know it or not. If you're relying on any of our managed services, most of them are built on top of EC2 and EBS. And in fact, we'll go through a little bit deeper design discussion into RDS, which is built on EC2 and EBS later. So things like RDS, Elasticsearch. Those are all services that are built on top of EBS, and they transparently take some of these lessons about failure reduction and make it so that you don't have to think about it. So just a little bit of introduction. An EBS volume is a durable block-level storage device that you can attach to your EC2 instances. Once you create a volume, you can attach it to any instance, and it looks like an attached disk drive. EBS volumes are flexible, so you can dynamically change the size or the performance characteristics of that volume while it's attached. You can use EBS volumes as the primary storage for data that requires frequent updates, such as storage for a database application. You can also use them for throughput-intensive applications, things like performing disk scans for log diving. They persist independently from the lifecycle of the instance. And most instances that are launched today use EBS as their boot volume. As we'll see in a moment, EBS is a zonal service. This means you can attach multiple volumes to a single instance in the same availability zone. And depending on the volume and instance type, you can attach a single volume to multiple instances all at the same time. All in the same zone, of course, too. Kemi mentioned EBS is a large distributed system, and that's true. We've put a lot of thought and effort to build resiliency into EBS. So we design those components to operate and fail independently. As part of the creation of every single EBS volume, our service chooses a set of storage nodes to host your volume. These storage nodes are chosen to ensure the availability and durability characteristics for each volume are achieved. The volume is continuously monitored for degradation and repaired if necessary. Now, both storage nodes and the lifecycle management services that create volumes have fault isolation, running strictly within an availability zone. But it wasn't always this way. As we take a look at how we've evolved EBS, consider your own application and how some of these patterns might apply. Maybe not directly, but give you something to think about as you architect better for resiliency in the cloud. EBS began its journey with a single control application responsible for all metadata for all volumes in a region. Now, being software engineers, we creatively called this storage manager. And if you think back to how applications were built, you can imagine how we built it. It was a large database, monolithic Java application serving APIs and business logic, and it was responsible for everything that happened on EBS within a single region. We kept replicas in each availability zone for redundancy and for performance. Now, the EBS volumes themselves were stored on independent storage nodes. And these nodes are responsible for the replication, hydration from S3 if you create a volume from a snapshot, and presentation to your EC2 instance. When we first built EBS, we recognized the importance of keeping your data separate. Over time, we've assigned names to these two different components. And this is really a common nomenclature within AWS. The EBS storage servers are part of what we consider our data plane. The data plane encompasses the EC2 instance, the network that attaches the instance to the storage servers, and then the storage servers themselves, and the media that runs underneath them. Now, Storage Manager was our control plane. In EBS, the control plane is responsible for all lifecycle operations, as well as things like maintenance and repair, performance monitoring, and other workflows. Now, as we scaled, we added more storage, but we also had to scale our control plane. Since it was monolithic, our options were mostly limited to increasing the size and number of replicas of the database. At this point, we began to question our life choices. We knew we couldn't just get bigger and more powerful machines forever, and we knew that the features that we needed to add to EBS, developer agility, would also suffer. We knew with all the functionality, our service would be a lot less resilient as well. Now, resiliency and reliability are important to us, and they're also important to you. EBS thinks about reliability more like a distributed system than a storage appliance. First, we think about availability. We define availability as the ability to access the machines that host your data, and typically accounts for the network and uptime of our service, and also our lifecycle APIs, so the create, attach, delete, et cetera. Now, EBS is designed for 5 nines of availability, and we track this continuously and set alarms and targets at aggressive levels to ensure we meet those design goals. The second thing we think about is durability. And this is once we get the I/O request to the storage servers, can we get that request off the media? EBS has up to 5 nines of durability, which is significantly more durable than a typical disk, somewhere between 2 to 4% depending on the disk. Now let's take a look at how we've evolved our control plane design to achieve the availability. Scale brings both benefits and challenges. In EBS, we're constantly thinking about scale and challenging our assumptions, which leads us to how we evolve our architecture. Now, resilience is a large focus area. We know it's important for you that we're available. And so we originally built our data plane so that customer data was stored within an availability zone, as I mentioned before. As we grew, we realized that part of the metadata associated with the EBS volume was critical to the health of that volume. The configuration of which storage nodes store the actual data is important for both the repair service and your instance that's attaching to those storage nodes. When things fail, this realization led us to create a new configuration service, creatively called Configuration Manager. We also wanted to reduce the impact of failure of the service, or blast radius, to be more similar to the volume. So we took the first step towards creating a smaller blast radius zones by making EBS truly a zonal service at this point. Configuration Manager plays a key role in the attachment and repair of EBS volumes. And different volume types have different replication strategies, depending on their durability and availability requirements. Now, when we created Configuration Manager, we focused on reducing dependencies and interactions with other services. We wanted the availability zone to be the largest thing that could be impacted by any failure. By constraining its blast radius to a single availability zone, we're able to reduce the impact of failure, as well as reduce the scaling load on the service itself. Now, as we thought about these requirements and its critical position within EBS, we knew we needed to have robust replication both for durability reasons and availability reasons. After exploring the available options, we landed on a database that was backed by the Paxos consensus algorithm, ensuring that we can correctly know the set of hosts participating in a volume and are able to widely replicate the metadata for protection of that data. Now here we're happy with the improved scaling and blast radius reduction properties. So we started to think about the rest of Storage Manager. Now we could have stamped out storage managers in each availability zone, but we took the opportunity to reevaluate our overall strategy. We broke the core functionality of Storage Manager into a few discrete services, and we did this all online while the engines were running. By separating the functions of Storage Manager into smaller services, we were able to be more efficient. Not just having to scale everything, but only the things that are required. It also improved developer efficiency. because developers could focus on their core functionality instead of having to gain mastery of the entire control plane. And so as you think of evolving your applications, consider if there's an opportunity to leverage even smaller services and some of the benefits that come along with that. Now, each service that we add makes our distributed system more complex. So far, we've covered how we thought about improving reliability and reducing blast radius. But what about failure? As EBS becomes more complex, we need to think more carefully about recovery in case of failure, because we know failures will always happen. There's Murphy again. As we thought about this, we looked to other engineering disciplines. This time we landed on aviation, and loosely borrowed from the term static stability. So let's define static stability from the aviation sense. So most transport and general aviation aircraft are designed to be statically stable in pitch. And so let's consider a flight in my Bonanza here. We're happily cruising along at 4,000 feet on our way to the San Juan Islands in Washington for a nice little weekend vacation. At some point, a vertical gust of wind, probably coming up off the ground as the heat rises, pitches the nose up. So the plane's flowing like this. Now, because my Bonanza is statically stable in pitch axis, the aircraft all by itself will nose back down to the same attitude that it was before. Now, this is pretty cool, but how do we apply that to our services? As we define it within AWS, and especially EBS, static stability is the ability for systems to return to a steady state after a small disturbance. And it's something we think a lot about. Now, we design our data plane to recover from failure with as little human and control plane interaction as possible. Now, whether it's a network partition, a larger scale power outage, we've built our systems with the ability to recover to a steady state in mind. And are continuously improving that ability so that we have fewer and fewer dependencies in the mix. We want to make sure that EBS volumes that are attached are going to remain attached, able to serve I/O, and recover as soon as possible after the disruption. So when something pushes, much like when something pushes on the nose of my Bonanza, it'll pitch in the opposite direction, back to where it was. Availability zones have grown to be tens of data centers. As we've scaled, even a configuration manager for an availability zone was too big. So we set out to create even smaller boundaries. We asked ourselves, what's the smallest blast radius we could have? We made a key observation here. Instead of a typical database, where every client needs all the data, we recognized that each client only had a small and specific amount of information they needed. And we created a new term called a cell. For the configuration manager, we wanted the cell to be as small as possible. But how small could we get? We knew that by constraining the data in the database, we could reduce the blast radius. We found is that we could build a database for every single volume. And so this leads us to millions of tiny little databases. The only clients required for each database is the storage server hosting the volume, the EC2 instance that has to connect to that volume, the volume itself, and the repair workflow. We built each cell as a 7-node Paxos cluster and are able to distribute the nodes both near the clients for availability and in neighboring locations for durability. And we only need a simple majority of the cluster to reestablish those attachments, giving us a small number of things in the recovery chain, leading to a more stable and available data plane design. Now, failures aren't just limited to the control plane services, but also the data plane as well. The original EBS had pretty simple replication across pairs of storage nodes, and we relied on complex infrastructure configurations to reliably ensure data durability. We also knew that we were going to want to add volumes that were larger and had a higher durability than the current products. Once again, we challenged our assumptions, this time around data resiliency. One of the things that we did is we created smaller data shards. These shards have a maximum size, which allows us to reason about the cost of repair as we think about our software and our hardware designs, while not limiting the volume size to any single storage node can handle. And each shard can have its own replication strategy, allowing us to increase the durability, such as in IO2, our 5 nines durable product. Now, the other neat thing that is counterintuitive in this case is that we can take advantage of more storage nodes for repair. So when a node fails, we have a wider replication match, leading to faster recovery back to full durability. Let's take a look at what that looks like. So here's the repair workflow, simplified view of EBS with storage nodes. See a number of different shards. These are represented by the colored boxes, and each node can peer with several other nodes. And so in this example, simple one-to-one mirroring. Not all shards necessarily have the same peers, though. Say the node in the middle fails, or it's removed from service. Now, this could be a planned maintenance event, and this part is pretty important here. This could be a planned maintenance event or an unplanned hardware failure. We keep the workflow the same for both of those so that our operators can reason about it and so that our software is easier to deploy and manage. Can you imagine what would happen if we only changed one fork of the repair workflow and we had two different things depending on which way it was going? Wouldn't be good. So the impacted shards are marked for repair, and the repair process begins by identifying new candidate storage nodes. Once the nodes are identified, the mesh characteristics of EBS allow for the shards to re-replicate quickly to other hosts. Instead of bottlenecking all repairs on a single link, it proceeds in parallel. Now, since EBS is a large distributed system that provides network-attached storage, we're hugely dependent on our network infrastructure. When we launched EBS, we started with a pretty basic protocol based on TCP. There's a few challenges. It's difficult to offload in hardware and can have some bottlenecks. It also takes a longer time to recover when there are failures within the network. It doesn't take full advantage of the way we build modern data center networks. Now, if you watched Peter's talk on Monday, you may remember SRD. And he described how it helps us improve tail latencies, but it's not just for performance. It was built to take advantage of our networks that have multiple points between two endpoints. SRD is continuously traversing multiple paths, quickly detecting and routing around failures, even in a full network partition, which are increasingly rare with modern designs. SRD will quickly probe and recover from that outage, all without overwhelming the endpoints in a thundering herd. So that's some of the things we've done in EBS to build resiliency into our service. We spent a lot of our time in iterating and improving the service to take care of the underlying infrastructure so you don't have to worry about it. This means you can focus your time and effort to improve your resiliency posture at the layers that you control. Much like security, resiliency is a shared responsibility. So in addition to building resiliency into EBS, we also give customers tools and capabilities to give you the flexibility to design a resiliency strategy that's custom tailored to what each of your services need.
Okay, so talk about capabilities and some things you can do to add more resiliency to your application as you build on top of EBS. So I'm not going to spend too much time talking about the different EBS volume types. Hopefully you've been to one of our other sessions, or you can just easily find this information online. But for this resiliency discussion, I really want to emphasize how important it is that you choose an EBS volume type that matches the criticality of your workload. Our general purpose volumes, GP3 is our latest generation general purpose volume, they're great for workloads that can balance price and performance. But that's not every workload. That's the majority of them, but that's not all of them, right? And so it's really important that you ask yourself this question. Would your customers or your business be impacted by a degradation or an outage of the service? And if the answer to this question is yes, you have what we call a mission-critical workload. And these workloads should run on IO2 or IO2 Block Express. Two reasons for that. First, Mark talked a little bit about this. IO2 and IO2 Block Express are our higher durability volume type. They offer 5 nines of durability. That's 100 times better than a general purpose volume. And second, they offer better latency consistency. IO2 Block Express in particular, it delivers the highest EBS performance, up to 256,000 IOPS on a single volume, with some millisecond latency. And so it's a really good fit for workloads that are particularly sensitive to tail latencies, like mission-critical databases, for example. So choose the right volume type to match the criticality of your service. Second thing I want to talk about, back up your volumes with EBS snapshots. EBS snapshots are a built-in, fully managed backup and restore service that we offer as part of EBS. It takes point-in-time copies of your EBS volume. Those snapshots are stored in S3, which is a service with 11 nines of durability. And these snapshots are incremental, and they're also crash consistent. And you can take a snapshot of all the volumes attached to your EC2 instance, or just a subset of them. You can do this with a single API call. It's super straightforward. And those snapshots will contain all the data you need to recover a volume. So if your volume fails, single API call, you can restore from a snapshot. And you can copy these snapshots across availability zones. and create new volumes from them. You can also copy them across regions. Snapshots is actually a regional service, so it's super easy to copy across regions. There's a few ways you can manage your snapshots. We recommend Data Lifecycle Manager, which is a free capability we have in EBS, and it allows you to create policies so that you can then create, delete these snapshots on a schedule or based on an event, triggering event. And we also offer AWS Backup, which is an automated recovery, backup and recovery solution across multiple storage types in AWS, including EBS. Next, I want to talk about redundancy. Super important to architect your workload to be resilient. Before I cover some ways you can do that, first I want to talk about what not to do. In an on-premises environment, it's very common to use RAID 1 for higher durability. But in EBS, this won't necessarily work. In fact, RAID 1 is what we call an anti-pattern. First, because it halves the EBS available bandwidth, because when you're writing to multiple volumes simultaneously, you're going to use more bandwidth, right, between EC2 and EBS. And so you either need to over-provision on your EC2 instance, or you just accept that you're going to cut your performance in half. But perhaps most importantly for this conversation is what Mark talked about when he covered durability. He explained how behind the scenes, we make sure that your volumes are placed in a way that meets the durability targets for the volume type that you choose. And we do this by replicating data across multiple servers in the same availability zone. This actually makes EBS volumes at least 10 times more reliable than a typical commodity disk drive. But it also means that parts of your volume, or two different volumes, might end up on the same storage infrastructure. So when you RAID 1, you can be inadvertently creating a shared fate situation. So it won't necessarily help. The way to think about it is let EBS handle redundancy at the storage layer. Thinking back to that tech stack that Mark shared earlier, let us handle the redundancy at the storage layer, and then you can focus on how you can build redundancy on the layers above that. So let's talk about some ways you can build redundancy. First and foremost, make sure it is across availability zones. As Mark mentioned, we put a lot of effort into making EBS a zonal service so that you can take advantage of that availability zone independence and build a more resilient architecture. This gives you a lot of flexibility when you're thinking about redundancy. So no matter which approach you use, make sure you're replicating across AZs. So a few ways you can do this. We actually recommend the most efficient way to build that redundancy is at the application level, because your application it has awareness of the semantics of your data, right? So we can optimize the path for that replication. Many commercial applications offer application level replication. Alternatively, you can do operating system level replication using a tool like DRBD. We also have a service in AWS called Elastic Disaster Recovery, and that's a good option if you have an RTO of minutes, and they can recover your data from the most up-to-date state or from a previous point in time. And then, of course, you can use snapshots and create volumes in different availability zones. All right, monitoring. Monitoring is super important. We run into a lot of customers that are not even aware that you can monitor your EBS performance with CloudWatch metrics. We have a number of EBS metrics available in CloudWatch. At a high level, there are 3 ways that you can monitor EBS performance. First, at the individual volume level, and you can monitor your volumes at a 1-minute granularity for volumes that are attached to an EC2 instance. And you can do some interesting things with those metrics. For example, you can monitor latency, and then you can set alarms that trigger based on whatever threshold you set. You can monitor the queue length for I/O, and that will tell you the number of I/O requests that are waiting to be completed. You can also monitor performance, throughput used. That's a good metric to monitor to make sure that you have sufficient provisioned performance to meet the demands of that workload. And you can also monitor at the EC2 instance level. And in this case, the metrics will compile usage for all EBS volumes attached to the EC2 instance. And then you can also do custom CloudWatch metrics. And you can do that by installing the CloudWatch agent in the EC2 instance. And that will give you metrics with 1 second granularity. Testing, also super important for a resilient architecture. And we wanted to talk about this because this also is one of those things that look very different in an on-premises environment than it does in the cloud, than it does in AWS. So you can take advantage. We have a lot of products and services that can help you validate your recovery procedures, right? In an on-premises environment, testing is usually done to prove that your application will work in a particular scenario. But one of the unique advantages of operating in a cloud environment is that you can test how your workload fails, and then you can validate your recovery procedures based on that. You can use automation to simulate different failure scenarios. You can recreate scenarios that led to failures before. You can create capacity to do that and then delete that capacity. So it gives you a lot of flexibility with testing. Some best practices for testing. I wish I didn't have to say this, but I still see a number of customers doing this. Always run your tests in a different account separate from your production environment. You can do this very easily with EBS if you copy your snapshots across accounts and then create a new EBS volume in that test dev environment account. And the other important thing to remember with testing is that as it happened with EBS, as your business grows, as your services scale, your architecture will probably change to support that scale. And so make sure you go back and test all those recovery workflows, all the procedures that you had put in place. As your architecture evolves, go back and make sure they still work as you expected and you can still meet your availability targets. All right, finally, let's talk about recovery. Earlier, we talked about understanding the risks in your environment and how they may affect the availability of your systems and how keeping in mind business criticality of your application and your availability requirements. Based on all of that, putting that all together, you can define thresholds to trigger some recovery or workflows. And then based on your assessment of your potential disruptions on your system, you ideally automate some recovery workflows based on the most common disturbances that your system may be subject to. Again, we have a number of capabilities that can help you with your recovery. Talk about some of them today. CloudWatch alarms, so monitoring of your EBS volumes, and then you can define recovery triggers based on latency, for example, or queue depth. And you can set alarms using CloudWatch and then use Lambda functions to build these recovery workflows on top of that. EC2 auto recovery is also something that you can trigger based on a CloudWatch alarm. And the great thing here is that the recovered instance is identical to the original instance, including the instance ID, private IP addresses, elastic IP addresses, all the instance metadata. So it makes it super seamless. Auto-scaling groups, another interesting capability to keep in mind. You can deploy, using load balancers in an auto-scaling group, you can deploy a group of EC2 instances across availability zones. The interesting thing about an auto-scaling group is it maintains a fixed number of instances in that group. And so even when an instance becomes unhealthy, it will terminate the unhealthy instance and launch a new one to replace it. And this is great for workloads that can recover in a few minutes. It works really well. But the other thing to remember is that auto-scaling groups rely on the same APIs that you would use to launch the EC2 instances yourself. And so if that API is experiencing an issue, if that API is not available, auto-scaling is not going to help you with your recovery workflow in that case. So alternatively, depending on your availability requirements and how quickly you need to recover, you might want to have that extra capacity pre-provisioned in a different availability zone, both on the EC2 side and on the EBS side, instead of relying on control plane operations. Now, this, of course, comes with a trade-off, because it will make you statically stable to the loss of a single availability zone, but you will incur additional cost to have that pre-provisioned capacity. So again, something that you need to weigh against the criticality of your service. For disaster recovery, copying snapshots across regions is also a common practice. You can copy that to a different account, as I mentioned earlier. And then lastly, fast snapshot restore, or FSR, as we like to call it. So when we create a volume from a snapshot, we perform an operation that we call volume hydration. And that basically means pulling your data from S3, where the snapshot is stored, into an EBS volume. And we lazy load that data so that you can start using that volume immediately. But you can see some latency while that volume hydration is happening. With FSR enabled, you can create a volume from a snapshot that is fully initialized at creation, meaning we don't need to pull that data from S3. And so this eliminates that I/O latency when you access the block for the first time, and your volume delivers the provision performance instantly. So all these features, they can help you fine-tune your recovery workflows, depending, again, on the criticality of your service. But the single most important thing about recovery is that you have to have a failover plan, and you must be willing to execute that plan. Having the right architecture is super important, is where we spend a lot of our time. But just as important is having a clear plan for when to fail over and how to fail over. When Murphy's Law strikes, you want to be ready to deal with it. And you don't want your team to be stuck in an ambiguous situation, right? And we often see that customers really contend with the decision, should I fail over now? Should I wait for infrastructure to recover? Don't be in that situation. Let me make this easier for you. The most resilient architectures that we see are from customers who can separate their recovery from our recovery. And so this means you need to decide up front how long you can afford to wait, and then be willing to fail over if you hit that threshold. And this is regardless of where in the tech stack that failure is happening. The way that that failure presents itself in your application is what should guide your decision of whether to fail over. Now, Mark is going to cover some examples of how all of this can be put into practice.
Cool. So most of you have at least one application that requires a database. And most of the time, you're going to put critical database into that, or critical data into that database, and data that your business depends on. And so it's a great place to explore resiliency, right at the foundation. And it often has some low-hanging fruit. Now, Amazon RDS is a fully managed relational database service that's built in AWS on top of EC2 and EBS. And the nice thing about RDS is that they have to operate a lot of customer databases on a daily basis. So you know they're looking for the best ways to minimize the impact of failures to their customers. So it's a great place to look for a reference architecture. Now, some of the choices they made around things like replication technology only make sense given their product requirements. But we can dive a little bit into their multi-AZ architecture and gain a few insights that'll help you build your database in the cloud, assuming you still want to run it yourself. Now, RDS starts with identical instances in each of 2 or 3 availability zones. One instance is selected as the primary. This is the one that your application does all of its writes to. RDS databases have some optimizations that are available to them that improve the performance, but in all cases, when the application needs to commit data, the primary receives the write, sends it to the secondaries, and it doesn't acknowledge it back to the application until the write is durably written. So when you're thinking about replication in a database like this, you have a few choices, each with pros and cons. You can choose generic block-based replication software. Now, the benefit here is that you can build common replication infrastructure, not just for your database, but for other applications as well. You can configure it once, and then create an AMI that you can deploy all of your other applications or containers if that's how you're deploying on. Now, block-based replication may cause a little bit of a performance degradation compared to application-specific replication. Application-specific replication, on the other hand, can be more complicated to set up and get right because you have to do it for every application that you run. But it often has semantic knowledge of the data. And so it doesn't replicate every single I/O naively, but only the really important ones. Now, RDS leverages their own replication that's similar to block-based replication so they can have a common foundation. But they've altered it so that it makes decisions based on the configuration of whether they have 2 or 3 availability zones and whether there's local SSDs available for them to cache writes on some of the secondaries. Now, the local SSDs will survive an instance reboot, but maybe not a hardware failure. It forks those writes in parallel, but only waits for a majority of them to acknowledge the write back. And so we can consider the RDS architecture as kind of a North Star. But I bet a lot of you have older applications that are hard to modernize. Maybe it's one that was first deployed in 1995. The vendor hasn't modernized it because, well, they haven't had to. Maybe you've got a single SQL database sitting in the corner closet that runs an entire business using a bespoke application created by a contractor that's long since retired. Let's face it, these applications, they're critical to your business. But they're tough and maybe even scary to move into the cloud. They might rely on things like single static IP addresses, may not have application level replication available, may have disk level redundancy, but more likely operate on a big expensive SAN. While it takes a little bit of work, it's not actually too bad to move these over to the cloud. You don't have to make all the changes at once. Just like if somebody asks you, how do you eat an elephant? You do it one bite at a time. The cloud is different, but it's important to recognize the advantages as well. No longer does a computer failure require you to call the manufacturer and wait hours or days, depending on your service contract, for a replacement. Instead of a vendor, there's just an API that you call to get more capacity. Not only can we provide alerting and monitoring to let you know when there is a failure, because they do happen, replacement host is just a few clicks away, and maybe even automatic if you've got it set up with the monitoring that Cami talked about. If you do have that single static IP, for example, don't rely on auto-assignment when you create an instance. You can use elastic IPs so you can move it to a different instance if you have to recover outside of auto-recover scenarios. On the storage side, EBS provides multiple levels of durability. As Cami mentioned, it's really important to choose the volume type that matches the criticality of your application. But not all the volumes attached to your instance have to be the same. General purpose volumes are great, but if you do need that higher durability or better performance, look to provision IOPS. Also, don't forget to build a plan for RPO and RTO. Snapshot automation with DLM helps. Really easy to set up and can allow you to recover faster into a different availability zone. If you can, set up application level replication. But if you can't, at least set up generic block level replication into another AZ. You might even be able to trick that application that thinks there's only one computer in the world to being a high availability application. Putting this all together, we've got the tools to help you develop a recovery plan, to monitor your volumes so you know when you hit your thresholds, define when to time out and alarm on it, and set triggers for those recovery workflows. If you remember nothing else, think about your availability plan before you need it, and don't be afraid to execute it. And most importantly, separate your ability to recover from our ability to recover. Thanks. We're going to be around outside for a little bit for questions if anybody's got them.